Hello everyone. Good morning. Yeah, sorry for my delay. So today we will talk about some examples on rule of thumb and rule of product. So this is the first thing that I prepare for you. So here in this problem we have a ladder. So this ladder has n steps. So 1, 2, 3, 4, 5, 6 steps here. And suppose that a particular person will always go up this ladder, either each time 1 step or 2 steps, always going up. We want to find out how many ways that this person can reach the top. Okay, so let's see a particular example of what we mean. So when n is equal to 1, n is equal to 2, and n is equal to 3, let's count what can happen. So when n is equal to 1, let's say we just have 1 step, then there is only one way to go to the top. So you just walk 1 step. So there's just one way. And if there are 2 steps, so how many ways are there? So if there are 2 steps, then the number of ways is you can either go 1 and then 1. So this is the first way, or you just go 2 steps. So in that case, this is going to be the second way. So here, when n is equal to 2, the number of ways will be 2. How about n is equal to 3? Now n is equal to 3, then we can think of it, there are even more ways. So one possible way to go is you go 1 and then 1 and then 1. So this is the first way that we can do. Or we can first go 1, but after that we go up 2. So 1 plus 2. This will be another way. And there's one more way. We can go up 2 first and then go up 1 next. So in such a case, then we can enumerate all the possible ways to go up the stairs with 3 steps. When n is equal to 3, there are exactly 3 ways. How many ways to reach the top? Now, to analyze this problem, we can somehow think about this a little bit cleverer. Suppose that somebody has already told you, let's say here, when n is equal to 2, there are 2 ways, and when n is equal to 3, there are 3 ways. Can we find out how many ways when n is equal to 4? Now, when there are 4 steps, okay, or in this particular, so imagine there are just 4 steps here. 1, 2, 3, 4. There are just 4 steps here. Now we can imagine what will happen. Okay, for the first step, the person can either go 1 or go 2 as his first choice, right? If the person go up 1 step in the first choice, then he will have 3 ways to go up in the remaining one, because after going up 1 step, there are 3 steps remaining. So there are going to be 3 ways, because we know that when n is equal to 3, there are 3 ways. Or the person can go up 2 steps as the first choice, and after that, there are 2 ways that he can choose. It is because after going up 2 steps in the first choice, there are 2 steps remaining. So there are going to be 2 ways. Now, in general, if we use W of n to denote the number of ways to move up n steps, then these are the numbers that we have computed already. W1 is 1, W2 is 2, W3 is 3. And Wn, as our case, it will in general be the number of ways to go up n minus 1 steps plus the number of ways to go up n minus 2 steps. This is actually, we are using the rule of thumb. To go up n steps, let's consider what is the first choice. If the first choice is 1 step, then there are going to be Wn minus 1 ways. And if the first choice is 2 steps, there are going to be Wn minus 2 ways. So in general, so there's a table here. So in general, Wn will be equal to 1, 2, 3, 5, 8, 13, 21, and so on. So what is it? So this sequence, forget about the first one. The first one actually represents W0, okay? So here we can see that this sequence is actually the famous Fibonacci sequence. Now, if you understand how to solve this problem, then it will be very easy for you if we change this problem slightly. Suppose that each time a person can go up 1 or 2 or 3 steps. Then is it possible to find out how many ways for this person to reach the top? Then in that case, we will need to find out how many ways that he can go up 1 step. If n is equal to 1, n is equal to 2, n is equal to 3, and based on them, we can find out what is the case of n is equal to 4 and 5. So I'll leave this for you as an exercise. In particular, for this problem, actually, we can define what happens when n is equal to 0. Okay, when n is equal to 0, there's no steps here. Then we can say that somehow it is equal to 1. There's one way, because the only way that the person can do is he does nothing. Okay, so this is the only way that he can do to reach up to 0 step. Okay, so W0 you can say it is equal to 1 as well. So in that case, if we add up the case of W0, then the full sequence will be 1, 1, 2, 3, 5, 8. So we have W0, W1, W2, and so on and so forth. Okay. Next, let's see another problem. Okay. Now this problem is we have a 2 by n board. So this is a 2 times n chessboard. And we want to cover this chessboard completely by using exactly n domino pieces. So a domino piece has exactly 2 squares. You can place a domino piece vertically or horizontally. So how many ways to fill the board? So the board has 2n area in total, but each time a domino piece cover 2 unit squares. So in that case, we will have n pieces, so it will be used to completely fill up this board. So here we use an to denote the number of ways of doing so. So we can compute a of 1. So a of 1 is what? 2 times 1. So the board is like this, 2 times 1. 2 times 1, there's just one way. You have a domino piece placed here. This is the only way. For 2 by 2 and n is equal to 2, then there are 2 ways. You can place a domino piece here, or vertically, both, or you can place domino pieces horizontally for both. So there are exactly 2 ways. And we can actually talk about A0. A0 is equal to 1 when you don't have any board. The only way that you can do is you do nothing. Okay. So A0 we can say it is equal to 1, A1 is equal to 1, A2 is equal to 2, and in general, what is AN? Now to solve this problem, we can think about this using the same idea as we used before. What we are going to look at is, so in the climbing stairs problem, we are looking at what is the first choice, and here we do the same thing. We want to find out what can be happening at the first column of this board. One way is we are going to cover the first column, so there are squares on the first column, by using a domino piece placed vertically, right? So this, we call it one case. And the other case is, so we are not going to cover the 2 squares here by vertical domino. So in the other case, we must be covering them using horizontal domino. And if we place a horizontal domino here, it must also be a horizontal domino here. Is that okay? So what we can have for the first column, if we watch only the first column, either the 2 squares are covered by the same domino piece, and in that case, the number of ways of doing so is whatever the number of ways that you can fill up the remaining part with n minus 1 in length. Okay? Or the other case is you are not going to cover the first 2 squares by vertical domino pieces. So in that case, it must be covering by the horizontal ones, and it must be covering like this. Is that horizontal here and horizontal here? And in such a case, then the total number of ways will be we cover the first 2 columns by horizontal domino pieces, and then we will cover the remaining n minus 2 columns by whatever way that we can have. So again, here the number of ways that we can do here is an minus 1 ways, and the number of ways that we can do here is an minus 2 ways. So again, we have an is equal to an minus 1 plus an minus 2, and amazingly, we get the Fibonacci sequence again. Okay. Now these two are fairly easy example, but if you have not seen this before, maybe it looks quite challenging. But somehow, if you have seen these type of problems before, then you can think about solving a big problem by dividing it into smaller subproblems. So this is the idea of having induction or recursion, right? So this is like a mathematical induction case. We are proving the n is equal to k plus 1 case based on the n is equal to k case. Okay, similarly, we are solving the problem of counting when we have the parameter n by the previous terms. And this type of technique is also called establishing a recurrence relation. Okay, so we are recurring that has appeared somewhere before. Okay, so the next problem that I will give you is more complicated. And this time I will leave it for you as an exercise. Now the next problem is we will not just need rule of thumb, but we will also need rule of product together. So let me define a term called balanced. So we have parenthesis sequence. We have a sequence formed by parentheses, and it is balanced. So if the number of opening parentheses is equal to the number of closing parentheses, also at any time, if we are reading from left to right, the number of opening parentheses has to be greater than or equal to the number of closing parentheses. So this may be difficult to imagine, but I will give you an example. So this is what we do in our daily life. So in this example, we want to ask which of the following sequences of balanced parentheses are, so which of the following sequence of parentheses is balanced? So here it is open, open, close, open, close, close, open, close. Is that okay? So this one is a balanced parenthesis sequence. So for balanced parenthesis sequence, opening is equal to closing. So 1, 2, 3, 4. There are 4 opening, and 1, 2, 3, 4. There are 4 opening, and 1, 2, 3, 4, 4 closing. And if we read from if we start reading from left to right, the number of opening here is 2, and then is 1, and then 2, and then the number of closing is 1. The number of opening is now being 3, and then it now 2, and so on and so forth. We can check that the number of opening parentheses at any time is greater than or equal to the number of closing. If it is a balanced parenthesis sequence, we can match the open with the close like this. So here we can match this open with this close. Is that okay? And then we can match this open with this close. And then we can match this open with this close. We can match this open with this close. Is that okay? So there is a way that we can do the matching. Now the next one here is not a balanced parenthesis sequence. So although we know that the number of open is 2, the number of closing is 2, so it's the same, but it doesn't follow the second rule that at any time we will need to have open more than or equal to close. So just after reading the first one, we will see that the closing is strictly more than the opening. So in that case, this is not okay. Now this one is more complicated, okay? So we have open, open, close, open, 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 close, close, open, close, open, open, close, close, okay? So it looks like it's quite balanced, but if we count it carefully, the number of open is not equal to the number of close. In fact, we can see this. This open and close are matched together, and then we have this open match with this one. We have this open match with this close, this open match with this close, this open match with this close, but then we will not have anything matched with this one. So it is not a balanced parenthesis sequence. And for this problem, suppose that the number of opening parentheses is equal to n. We want to find out how many balanced parenthesis sequence we can form. let me give you a hint of how to solve this problem. Again, you can solve for the case when n is a small number. So we can solve for n is equal to 1. So if there's just one open, so one open, one close, we call it one pair of parentheses, then there's just one way. We must have open and then close. Now when n is equal to 2, there will be two ways. We can have open, open, close, close, or open, close, open, close. And when n is equal to 3, after careful counting, there should be 5 ways. So let me draw the case when n is equal to 3. So when n is equal to 3, it could be open, 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 close, close, close. Is that okay? So there's one way. Okay. When n is equal to 3, we can have open, close, open, open, close, close. This is another way. And then symmetrically, we will have open, open, close, close, open, close. There's another way. The third way, we can have also this one, open, close, open, close, open, close. This is a fourth way. And the fifth way is this one, open, open, close, open, close, close. So these are the cases when n is equal to 3. So there are 5 ways. So in general, how do we find out the number of ways of getting parenthesis sequence with n pairs? Now let me give you a hint. Okay, so first of all, I will classify this as the first type. We're using rule of thumb. So I'm going to classify them into different types. So this is going to be my first type. So I will explain to you why. So this is my first type. And then I will say this is also the first type. And then these two are my second type. And then finally, we have the third type. Okay. So, okay, so if I'm coloring the types in the same color, so these two are following in the same color. These two are my second type. And then this one is my third type. Okay, so, okay, now let me tell you how I'm classifying the parentheses. So as we recall, every opening will have a matching. So the first opening must be finding some way to match in the sequence. So this opening is matched with the last closing. This opening is also matched with the last closing. So these two, I will call them type last because the opening is matched with the last one, the third one, right? Now these two are, the opening is matched with the first closing. There are 3 closing, right? This is matching with the first closing. This opening is matching with the third closing, first closing. So I will classify them into the same type. And this one, this opening is matched with the second closing. Okay. Now, how many ways are there for this type? If the opening, the first opening is matched with the last closing, so the number of ways is how many ways that we can arrange when there are n-1 pairs of parentheses. Is that okay? Now for this one, this has to be matched with the closing, right? The first closing. So again, how many ways? So after the matching here, so how we can arrange the remaining part with n-1 parentheses, then we are done. So there are 2 ways here, then you have 2 ways. So you can see that this one, there are 2 ways because after removing the matching parentheses with the first one, the remaining part is the case with n-1 parentheses. Similarly for this one, it is the case for n-1 parentheses. But then we consider this case and this case to be different because it is a different closing parenthesis that is matched with the opening. Now, how about this case? For this case, the first opening is matched with the second closing. Okay, so the number of ways here is the number of ways to arrange one pair, and the number of ways of arranging one pair, and then what? Because we have any choice of arranging one pair here, and any choice of arranging one pair here, so the number of ways is the number of ways to arrange one pair multiplied with the number of ways of arranging one pair. So we get the rule of product to be used here. So I'll let you find out the general the way of computing the next term. And if you have time, we will talk about this during the next tutorial. Okay, so that's all for today. Yeah, thanks all for coming. Let me check if you have any question. Yeah, thanks for coming. Okay, and then if you are interested in this problem, you can search for this particular term. It is called Catalan number. Okay. I will explain a little bit more when we have time. Yeah, thanks so much. Okay, so let's end the tutorial now. Thank you.